All right, section 1.7, day 1. Today we'll be working on using vertical and horizontal shifts to sketch graphs of functions, mainly just some parent functions, along with what I'm going to call generic functions. And we'll also work on reflections to sketch graphs of functions as well. Okay, the non-rigid, multiplying by a number to change the shape of it. We'll wait till day 2 on that. Okay. All right, we've been moving around and graphing a lot of linear functions. So we still have to be able to recognize them from section 1.6, but we aren't going to translate a bunch of those. We will be focusing on translating quad functions, cubic functions, absolutes, square root functions. But that'll be about the extent of that. We're not going to rotate or translate reciprocals or step functions. We'll also move around some generic looking functions, but what I mean by that is if I skip ahead to 2 pages, we kind of see this. It doesn't look like an absolute or quadratic or anything. This is just kind of a generic graph. We're given some coordinates to translate. We'll be working on that as well, okay? Okay, so for vertical and horizontal shifts, you want to recognize the difference of the placement of the constants. So for horizontal shifts, we have to look for a number being added or subtracted inside the function. Okay, so if it's subtracted inside the function, it's always going to move it horizontally to the right. If we see a number being added inside the function, it moves it to the left. Horizontal, students like to remember this as opposite the sign. Vertical is a little more true to the sign. So if I add a number outside of the function, so by inside and outside, let me just show you real quickly what we mean by that. Let's just say we have a quadratic. You don't necessarily have to write this down unless you want to. If it's outside the function, it look like this. Okay. If it's inside the function, it look like this. Okay, so that's what I mean by inside for these 2 examples, and then outside for these 2. Okay, so when we add a number outside, it is going to move it vertically up. Okay, if we subtract the number on the outside of the function, then we'd say it moves vertically down. Okay. All right, not a brand new concept to you guys, so hopefully this will go quick and easy for you. The reflections and things like that get a little more difficult. Okay, so step 1 here on this first example says identify the parent function, then graph the equation using transformations of the parent graph. All right, so the first thing you want to do is always, I want you to write this down as kind of your first step. Get good coordinates to translate. Get good coordinates to translate. All right, so identify the parent function. If we don't have the +2 there, we just have f of x equals x squared. So the parent function is y equals x squared. And what I want you to do next is to get some good coordinates to start with. All right, so typically 1 negative, 1 positive, and 0 works for a lot of these parent functions. Not all of them, but for a lot of them, I think using -2, 0, and 2 are a good idea. So for the parent function, don't do the +2 yet. We're just focusing on this. So -2 squared is 4, 0, and we get 4 here. So let's plot these coordinates of our parent function. And then you're expected to remember the shape of the quadratic function as a parabola. So kind of horseshoe this thing up a little bit, like that. All right, and then this plus 2, we got to recognize this as being on the outside of the function, not the inside. If it was the inside, we'd see something like this on number 2, right? That's inside. This is outside. So we need to realize that this is going to be a vertical shifts up 2. All right, and this is rigid. It's not going to change the shape. So all we have to do is pick up this coordinate, move it 2 units up, and drop it back down for all 3 of these. Okay. All right, so that one just had 1 step. Sometimes we have 2, like we do in number 2. Okay, moving on to a new parent function for number 2. Now we notice an exponent of 3, which changes it to a cubic function. Okay, so y equals x cubed is the parent function. We need to get good coordinates to translate and move around. Once again, I like to just stay consistent on this step for you guys. Let's stick with -2, 0, and 2 as our input values. -2 to the 3rd power is -8. 0 cubed is 0, and 2 cubed is +8. All right, this slides off this coordinate plane a little bit, but we can still estimate where it's going to be at. So here's -6, go down about 2 more units to there. 0, 0, and then 2 8s. Okay, so if we peek at the previous page, you forgot what the cubic function looks like. All right, it increases pretty fast. It slows down through the origin, and then it picks back up as x increases again. All right, so just show a little bit of a bend. Shouldn't see a straight line through these 3 coordinates. I should see some attempts at a bend. So increase quickly, bend through the origin, and then increase it rapidly again. Okay, I like that. Okay, and then we got to remember these different translations. When we add 2 inside, this moves it left 2 units, and then the -1 outside is going to move it down 1. And you don't necessarily have to break this up into 2 unless you're more comfortable with that. We can do this 2 steps in 1. Okay, so if I'm going to go left 2, down 1, it's me about right here. Left 2, down 1. Continue that. Okay, I'll help you with the parent function on number 3, then kind of let you try this one on your own. Okay. So for 3, we got another new parent function, absolute value of x if we get rid of the horizontal vertical shifts. So you can peek at the previous page. If you need help seeing that again, it's that sharp V shape looking curve. Okay, is what we should see here. So let's get some coordinates that so we just don't wing this thing. Try to be accurate. Okay, so -2, 0, 2. All right, figure out what y is going to be. Get your parent function, and then figure out the final result. Okay, go ahead and give you about a minute or 2 to do that. Okay, there we are. Make sure it looks like a sharp V, not horseshoe or U-shaped. Here's the coordinates that I moved around. Okay. Right 2, up 3. All right, so why don't you try 4 and 5 real quick. Now we're just moving backwards. Now we're going to write an equation for this. These don't take long. So f of x equals x squared. What are you going to do? How are you going to write what translation you see from the parent function to this result? Same thing here. This one's going to have 2. Okay, it's moving right and down. Okay, give you about 30 seconds to a minute to write down the equations. All right, so compared to the parent function that I drew in there, if we go up 3 units, we see this result. So here's the answer to the function. Y or f of x doesn't matter. This one, if we compare it to the parent function over here, it's moved over 2 units and down 1. So here's the equation we should have for number 5. Okay. All right, the second learning target today involved the reflections over the x-axis and the y-axis. So here's the things we got to pay attention to for the difference. That's a reflection over the x-axis if we see a negative outside the function. So for example, maybe like the square root function, square root of x. If it's on the outside, we see it out here. And if it's inside the function, okay, it look like this. And if it's inside, it reflects it over the y-axis. Okay, so location of the negative is important, something you got to commit to memory to know the difference of the two. All right, so once you get that down, let's turn the page and take a look at the next 2 examples to wrap this up. Okay, and number 6 has a new parent function, so this is a good one. So our parent function is y equals square root of x. All right, here we don't want to have a negative x value. The other ones, negative 2, 0, and 2, work pretty good. But our parent function for the square root has a domain of 0 to infinity. Starts here. We can't take square roots of the negatives. So what you should probably do is start at the starting point of 0, and then just pick some numbers that have perfect square roots, like 1 and 4. You don't have to. If you want to plot some decimals, you could, but I would recommend using perfect square roots. So the square root of 0 is 0, square root of 1 is 1, and square root of 4 is 2. So let's plot those points. Okay, and you extend it through a little bit. Don't make it go down, because if you make it go down, it doesn't do that. Think about the next perfect square root. Square root of 9 is 3, so 9 3s out here. It's supposed to contain that point. So extend it up a little bit, okay? Okay, so now I have the parent function. When the negative's on the inside, what does it do? It reflects it over the y-axis. That's what it says on the other side, right? So when the negative is on the inside, reflects over y-axis. Okay, so I'm just going to take this coordinate 1, positive 1, and reflect it over this y-axis here. Same thing with 4, 2 becomes negative 4, 2. Looks like that. Okay. All right, for number 7, it has 2 of them. Reflection, always do the reflection first. Try to think of the order of operations when determining order of transformations. So your first step is going to be the reflection, and then your second step will be the shifts, the addition, subtraction. Okay, I'm going to keep this under 15 minutes. I'm going to pause it and then show you the end results after you try. Okay, so as I mentioned, if we do multiplication first, then I reflect the parent function. It's down here. Then I shift it up. So this is the correct graph. If you went the wrong order and shifted it first, then reflected it, we get this graph, which is incorrect. Okay? So got to follow the right steps.